Hello everyone. So I decided to um, let the next topics for this class. So let's start it. We'll today we are going to talk about explicit and implicit numerical methods, also about local truncation errors, global errors, and convergence. So consider the initial value problem. As we said, we have here ODE, and we have an initial condition for T0. And for simplicity, we are going to choose T0 equals 0, okay? So, and K will denote the time steps. So that our Tn will be T0 plus Nk. So what does it mean? It means that we are getting our time interval that we are looking for the solution here. Okay, so let's suppose that we want to approximate the solution at the interval t0 t, big T. Setting t0 equals 0, so it will be the interval 0t. So what we do, we get the interval 0t, 0t, and we divide it in, let's say, into any subintervals. Okay? So our k, it will be t minus 0. It could be t0 if t0 is different than 0, divided by the number of subintervals here. Okay? And then, so we would have here T1, T2, and then here Tn for some n, okay? So our Tn, if we take T0 equals 0, our Tn will be n times k. Makes sense, right? So if we are at the time big N, so T N, it will be N times K. And it would be equal our big T, our final T. So this here makes sense. So given an initial data, u0 equal eta, so this is the initial condition. We want to compute approximations 1, 2, 1, 2, 1, u1, u2, satisfying that the big U is an approximation for the solution of the initial value problem at that point. So in the forward Euler or Euler's method, we talked about it some classes ago, 2 classes ago, and we even discussed how this method is, how we can intuitively, graphically have this method. So we just approximate by the slopes using first order Taylor polynomials. So if we have our initial value problem given by u line of t equal f of u t, here for t bigger than t0, and our u0 equal eta. Okay, so let's say that t0 is 0. Why? Okay, I don't know why it happens, honestly. So t bigger than 0. Okay. So substituting the Euler's methods into this initial value problem, how would it look like? So this is our method. So the first step is to define in which interval we are going to search for the solution. So we need to set an interval that we are going to approximate our solution. And then we choose the number of subintervals n, and then we calculate k equal t divided by n. Okay? That being done, that being said, we are going to iterate. So our u1, it will be equal the u0 plus the k. So what's our f? Let's suppose here that our f of u t just depends on u. It could be u square, for instance. So here we are going to substitute f of u1, so f of u0, sorry. So it will be u0 equal eta plus k times, so eta is square if our f is like this, okay? And then we are going to do it successively, and then the un plus 1 equal un plus k, un is square for this example, okay? And then it will stop here. So this is the last calculation. Un equal un minus 1 plus k un minus 1 square. This is explicit method. It means that you can determine the un plus 1 explicitly by substituting the solution on the last time, okay? And we can also have the backward Euler. So instead of calculating our f at the point un, we calculate at the point f of at n plus 1. So in our initial value problem, the past example, I said that our f of u equal u square, right? So our un plus 1, it's equal un plus k times un plus 1 is square. Now here it's this un plus 1 is also an unknown, so we cannot calculate un plus 1 explicitly. So what do we do? In this case, so imagine that un plus 1 is some incognite. So it's some x. We like to call x when we don't know the value of some. So imagine that you have some function here. In this case would be x minus k x squared. So un is known, so let's say that un it's equal some constant. Let's call it a. Okay, so a minus a equals 0. So for calculating un plus 1, we would need to find the root of this function here. Let's call this function g of x. Okay. In this case, in this example that I gave, we can analytically find the value of these roots because it's just a second-degree polynomial. But imagine that instead of having some function like this, u square, that we would have ln of x plus 1 divided by x square root of it. So something like this. And then here we would substitute, sorry, here it would be, so let's just suppose it. So that our f of u it's equal ln of x plus 1 square root of u. It's on u, sorry. Ln of u plus, okay. And here we would have ln of u n plus 1 plus 1 divided by u n plus 1 square root of it. And then if we call un plus 1 equal x, the unknown, our problem would be to find the root of the function g here, given by this x minus ln of x plus 1 divided by square root of x minus a. Okay, so equals 0. In this case, it's not so straightforward to find some x that satisfies this equation. And more than that, it's possible that on the interval that we are dealing with, we cannot because like it's also possible that we have more than one root satisfying this equation. In the other case, in the second degree polynomial, it was also true. But I'm going to show some examples and show how it can be done in practice. Okay, so usually instead of trying to find this root of this function g of x, so instead of solving g of x equals 0 analytically, we use the Newton method to find the zero of the function g given by this, okay, as I said. And then we have un plus 1. So the Newton method is only one method available. So, and it also has its restrictions. I'm going to talk about it at some point. Because it can also not converge in on the interval that we are searching for this root. So there are some practical matters here. So the question that you might be doing now is that, like, if we have the Euler method, why do go for implicit method? So this is an implicit method. So the answer is that there are some region in which the method is stable. So we are going to define what stability means. So it's for some kind of problems the explicit method cannot give a good enough approximation for our problem. So that's why we have to go for other kinds of method, okay? So, and another method, it's also implicit one, and it's kind of averaging the forward Euler and the backward Euler. And it is known as trapezoidal method, and or Crank-Nicolson. But the Crank-Nicolson usually it's known for when you use it to solve EDPs, some PDEs, some partial differential equation. So we see here that it's some average between explicit and implicit Euler. And again, if our f is nonlinear, we would have also to solve that some nonlinear equation to find un plus 1. So this this method that I showed here, they are all first order method, which means that at each time step, so to find n plus 1, we just use the solution at un. Okay, so it's a first one-step method. But it's also possible to do this approximation using other time steps. And then this is known as multi-step methods. And it can increase the order of the accuracy and involves other previous values. So in this case, for instance, let's give some example, okay? So we have the leapfrog method that's given by this. So observe here that to obtain the n plus 1, we are using also the n minus 1 and also the n. So if we start with n equal 1, okay, because n equals 0 is known, it's given by the initial condition. So a natural question would be, so how to proceed, because we would have something like u2 minus u0 divided by 2k equal f of u1, right? So we want to calculate u1, but we don't have it, u1 and u2. So the answer is that usually we use some other method to approximate u1. Okay, so it's like u1 is in approximation for an initial condition for this method. Okay, then you can use forward Euler or backward Euler, then you get u1, and then you can start using the leapfrog. So the leapfrog will start to be calculated only for u2. Okay, and then we have, so the leapfrog method, it is also an explicit method, right? So for un plus 1, you use past values here. Okay, and then we have the backward differentiation formula. This is an implicit, because here we have some relation involving the un plus 1, so we need to find it implicitly. So again, it involves n minus 1, so we need to first determine u1 using another method, another first step method. Okay, and then now we have the Runge-Kutta. You have probably heard of this one. I think that MATLAB function to solve ODE use some Runge-Kutta method, because the Runge-Kutta can be two-stage, but the ODE 45 from MATLAB use some fourth order Runge-Kutta method. Okay, so the Runge-Kutta two-stage is given by this. So it's a two-step. It means that first you calculate this, and then you put what you found in here. Okay, and here it to find u1, you don't need to use another method. Okay, you can just simply start with u0 here. Okay, and yeah, so this is also some explicit method. It means that for calculating un plus 1, you just need the things from previous calculations. So now we are going to start to talk about local truncation error, and it will be more clear. It will be necessary to identify which method can do it is related to the order of the approximation that we are having on our method.